Hey everyone, it is Mr. Prevet back again with another FRQ review for you guys. Today we're looking at the 2022 FRQ number 4. We got a table. Looking at the question, we got some Riemann sums, we've got some theorems, we've got some related rates, kind of filling in the gaps of like some more niche topics, which I think is really interesting. This is stuff that may not show up on every FRQ, but it's really important stuff to kind of fill in the gaps, specifically if you're like aiming to pass or be like a high passing score, the 4 or high 5. It's really important that you understand these topics because you can't just know what a derivative is. You got to be able to know your theorems, know some Riemann sums, related rates. This is all going to be really useful. So let's dive into the question together. So we got this table, and it's time versus r prime of t, which is centimeters per day. So it's some rate, right? So it says an ice sculpture melts in such a way that it can be modeled as a cone that maintains a conical shape as it decreases in size. The radius of the base of the cone is given by a twice differentiable function, r, where r of t is measured in centimeters and t is measured in days. The table above gives selected values of r prime of t, the rate of change of the radius, over the time interval from 0 to 12. Okay, so thinking about this conceptually, right, we have some sort of conical ice figure, right? It has a radius. And as it melts, that radius is decreasing, right? So we know that r prime of t is less than 0 because our radius is changing. So our rate of change of the radius will be negative over time. And it's decreasing all the way until t equals 12 days later, right? Okay. And looking at the table, this does kind of add up because all of the values of r prime of t in the table are less than 0. They're all negative values. So this makes a lot of sense just looking at it initially. But part A, let's go for it. So part A says approximate r double prime of 8.5 using the average rate of change of r prime over the interval from 7 to 10. Show the computations that lead to your answer and indicate the units of measure. Okay. So this is like the big takeaway that I have from these types of questions. This is a mean value theorem question because mean value theorem talks about if over an interval, if we're continuous and differentiable, there must be a point where our instantaneous rate of change equals our average rate of change, right? That's mean value theorem. But what it tells us is that when we're trying to approximate an instantaneous rate of change, a really good approximation is average rate of change. And the average rate of change of a function over an interval is f of b minus f of a divided by b minus a. Now our function in this case is r prime, right? So I'll do r prime of my second point on the interval minus r prime of 7 divided by our b minus a, which is 10 minus 7. So when I find the average rate of change of my first derivative, that's an approximation for my second derivative. Same thing if I found the average rate of change of just my r function, like r of t, that would give me an approximation for r prime. But we can solve this using the table. R prime of 10, it says is negative 3.8. R prime of 7 is negative 4.4. We'll divide it by 3. That's a double negative, so those will cancel. I'll get 4.4 minus 3.8, which is 0.6, divided by 3, which is equal to 0.2. But now it does say indicate units of measure. So we got to figure this out, right? Now, our radius is just going to be measured in centimeters, right? And then when I take the first derivative, I find that rate of change, I get centimeters per day. So when I'm looking at the second derivative, right, I'm going to get those centimeters per day, right? It's a rate of change of our rate of change. So my units are going to be centimeters per day squared, or centimeters per day, right? I like writing it in squared just because that's the general form you use in physics specifically. So those are our units, and that's our final answer. So the biggest thing for this one is just remember the average rate of change is a really great approximation for instantaneous rate of change, right? Specifically on the AP, whenever they ask you to approximate a rate of change, they're always going to give you two endpoints that have values where what you're approximating is like halfway between them. So like 8.5 is halfway between 7 and 10, right? If they wanted you to approximate it between 3 and 7, those are two more values on the table, they would ask you to approximate r double prime of 5, right? It's always going to be halfway between. It's just kind of how the AP rolls. So it's good to know that as well. But we'll move on. Part B. So part B says, is there a time between 0 and 3 for which r prime of t is equal to -6? Justify your answer. Okay, so let's check it out. Look and see, does r prime of t have to equal 6 at some point? Well, let's look at our table, right? Our rate of change of our radius goes from -6.1 to -5.1 to -4.1, on and on and on, right? So our rate of change is like going to be changing, right? But it specifically says that the radius of the base of this cone is given by a twice differentiable function. That means that our first derivative has to exist at every single point. It also means that our first derivative has to be continuous, right? If it's differentiable, that means our derivative is continuous, right? So r prime of 0 is down here at like -6.1, right? So if I were graphing like time versus r prime, but then at 3, we get up to this point, 3 comma -5.0. And our function, r prime of t, who knows what it looks like? Right? But it is a continuous function, right? And it's asking us, must there be a place where r prime is equal to -6? Oh, I'm sorry, I wrote 6 up there. I meant to write -6. And I would say the answer is yes. Because r prime of t is continuous, there must be a place between 0 and 3 such that r prime of t is equal to -6. And this is a result of a specific theorem. Hopefully you remember what it is. It is intermediate value theorem. And that is the key to this question. If you've seen this form before, like must there be a time? Generally, that's kind of code for you're going to use mean value theorem, Rolle's theorem, intermediate value theorem. They're kind of code words. And for this one, it's saying, hey, if we have these 2 points on the outside, does it have to be true that there is a point on the inside? The answer is yes, according to intermediate value theorem, because our derivative is continuous, there must be a point where r prime of t is equal to -6. So that was a tricky one if you didn't know the theorem. If you did know the theorem, relatively easy one. For that one, it's just really important. Like you gotta say the buzzword, right? You gotta say intermediate value theorem. If you don't say that, the AP is going to think you don't really know what you're doing. But if you say intermediate value theorem, you're going to be in a fantastic spot. Yeah, To earn the second point, the response need not explicitly name the intermediate value theorem, but if a theorem is named, it must be correct. Name it, you're going to get the point. That's the main takeaway from part B. Let's move on to part C. Part C, we get a Riemann sum. It says use a right Riemann sum with 4 subintervals indicated in the table to approximate the value of the integral from 0 to 12 of r prime of t dt. Okay, so a Riemann sum is an approximation for an integral, right? It takes like some curve, and it basically uses these little rectangles to approximate the area. Right? And sometimes it's an over approximation, sometimes it's an under approximation, right? And that depends on whether the function is increasing or decreasing. But for this one, it asks us to use a right Riemann sum, which means that when I take these rectangles, I'm going to use the value of the function at the right endpoint. So to approximate this, I'm going to take the length of my interval. So my first length is from 0 to 3, so its length is just equal to 3. And I will multiply that by the value on the right side of that interval, which is -5. The next interval is from 3 to 7, so it has a length of 4. And its value is -4.4 at t is equal to 7. The next one has a length of 3 as well. It has a value of -3.8. And then the final one has a length of 2, and its value is -3.5. So we got to use our big old math brains to multiply out some decimals, but this will give us -15 minus 17.6 minus 11.4 minus 7. Combining these together, those two is -22. Subtracting those two together, it's really like adding them, but that would give us -29, which is equal to -51, which would be our approximate value, right? For the integral from 0 to 12 of r prime of t. Now, I know it doesn't ask for it, but I want to think about what this actually represents in context. What is this -51? What are the units of this -51? Well, we are taking the integral from 0 to 12 of r prime of t dt. I know using the first fundamental theorem of calculus, this is our radius at t equals 12 minus my radius at t equals 0. We're saying that's equal to -51. So what this means is that my radius after 12 days is 51 centimeters less than it was at t equals 0. So my radius has decreased a total of 51 centimeters over this time interval. That is what this value actually represents. And even though, the AP doesn't ask it this time, it would totally be within reason to ask you like what this number represents. But that's all we got for part C. Some cool learning gains there. And now we move on to part D. So part D says the height of the cone decreases at a rate of 2 centimeters per day. At time t equals 3, the radius is 100 centimeters and the height is 50 centimeters. Find the rate of change of the volume of the cone with respect to time in cubic centimeters per day at time t equals 3 days. Okay, so this is a little scary, but we see like our radius and our height are changing at certain rates, trying to see what the rate of change of our volume is. That's kind of keying us into the idea of a related rates question. Now, our first step of a related rates question, I want to visualize what's going on. We kind of drew this before. Excuse my artwork. But we have a cone with a radius. We've got a height. The radius and the height are changing. They're both getting smaller as this melts. And our volume of the cone is equal to this equation they give us, 1/3 pi r squared times h. And that's our second big step of a related rates question. I want to get an equation that has all of the variables, right? Volume, radius, height. And now my third step, and the one that really starts to open things up, is that I take the derivative implicitly with respect to time. So on my left side, my derivative of volume is just dv dt. That is my rate of change of the volume. And that's what they're asking us to actually solve for, right? So we're not going to be able to just get this left side. We're going to need to calculate this right side. Now there's a pi over 3. I know using constant multiple rule, I can just factor that pi over 3 out, multiply it together at the end. So now I'm just looking at this r squared h, right? To take the derivative of r squared h, I'm going to need to use product rule because r squared is a function, h is a function. So I know product rule is first term times the derivative of the second term. Now the derivative of h, we're taking it with respect to time. So it's going to be dh dt. So that's my first one. The second half of product rule is the derivative of the first term, which would be 2r, but we gotta be careful, we're taking it with respect to time. So it's 2r dr dt times my second term, which is just h. So this is my whole setup, and now I see my rates, dv dt, dh dt, dr dt. Now let's see what the question actually gives us. It says the height of the cone decreases at a rate of 2 centimeters per day. Well, that tells us that dh dt is -2. It also tells us that the radius is 100 centimeters. So that radius is 100. So is that radius. They also tell us that the height is 50 centimeters, right? Now, the one thing that we don't have is dr dt, our rate of change of the radius at the time t equals 3. Now, the great thing is we look back at our table. What does our table get us? R prime of t, or dr dt, right? And this will give us a rate of change of our radius at t equals 3. We look back, it's equal to -5. So now I'm just going to plug all of these values in and solve for dv dt. So we gotta do some arithmetic. Still got that pi over 3. I'll get 100 squared, which is 10,000, times -2. So -20,000 plus 2 times 100, which is 200, times -5, which is -1,000, times 50. So -50,000. So I subtract those together. It's equal to pi over 3 times -70,000, which is -70,000 pi divided by 3. We think about units too, right? They give them to us, but it is cubic centimeters, which is my units of volume, per day, which is my units of time. So quite the mess, but thinking about this conceptually, it makes sense that this is a negative value, right? Because our cone is getting smaller, it's melting, right? So if we got a positive value for our rate of change of our volume, we would be really concerned. So it's good that we got a negative value. This answer definitely scary though, just because it's so big, weird fraction, but that is our final answer. So a good old related rates question to wrap this one up. But I hope this one was helpful. I really think that these were some cool topics that were talked about in this FRQ. Great practice for us. And yeah, hopefully this sets you up well for your future FRQs, future multiple choice questions that you may see on an AP test. But it was great going over this with you guys, and I hope to see you on another video real soon.